Hello, my name is Steve Ives and I'm with the Synergex Professional Services Group. I'd like to welcome you to Synergy DE version 9.1 highlights. This presentation is geared towards Synergy programmers who wish to learn about the new Synergy language features available in version 9.1 of Synergy DE. The development of Synergy 9.1 was the single largest development project ever undertaken by Synergex throughout the entire history of the company. Over 30 man-years of effort went into this release, and as a result, version 9.1 introduces some very significant new features. Perhaps the largest single new feature is the support for object-oriented development in Synergy language, but there are many other things to talk about as well. Many long-time Synergy developers believe that this is the most important release of Synergy that there has ever been. During this presentation, we'll focus on giving you an overview of many of these new features. However, we will be focusing mainly on the non-object-oriented new features of the language, although some OO will inevitably creep in. The support for OO development techniques in Synergy is covered in depth in a series of 3 Webucation presentations entitled Synergy Objects. For those of you who may be interested in the OO capabilities of Synergy version 9.1, let's take just a couple of minutes to provide a very high-level summary of what is now supported. Synergy language now supports a relatively comprehensive set of OO development techniques, and the implementation and support for those techniques has a very high level of compatibility with the capabilities of other leading object-oriented programming languages, such as C# or Java. Synergy supports all of the mainstream OO capabilities that OO developers would expect, including support for namespaces, classes, fields, methods, including constructors and destructors, properties, structures, static and abstract members. We have full support for inheritance and even support operator overloading. This is by no means a comprehensive list of what is supported, but it should be sufficient to reassure OO developers that the capabilities are fairly comprehensive. Synergy allows you to develop new 100% OO applications or to enhance existing procedural applications through the use of new OO techniques. We distribute a number of sample OO programs both online and as part of the product distribution. As mentioned earlier, the OO capabilities of Synergy language are addressed more fully in other Webucation sessions. It's simply not possible to try and cover all of the OO capabilities of Synergy language in a single session like this, so we're not even going to try to do that. Presenting too little detail about OO is dangerous. However, for those of you who may already be comfortable with OO techniques, I'll show you just a little peek at some Synergy OO syntax. The code on this slide represents an example of a class called order. As you can see, the class is part of the namespace called mycompany.ar. This class has 3 private fields called goods, shipping, and tax. The class also has a public method called calculateDiscount. The method uses the data in some of the private fields and returns a discount amount for an order. This slide shows a class which has a public read-write property called discount%. As is often the case, the property's get and set methods propagate the value of the property into a private field of the same data type as the property. Again, as a reminder, there are several other Webucation sessions which present Synergy object capabilities and syntax in much more detail. If this is something that is of interest to you, then please take time to watch those other presentations. For now, what we're going to do for the rest of this session is focus on all the other features introduced in Synergy language in version 9, apart from the OO stuff. Okay, let's leave objects behind for the time being and focus on all of the other new features in Synergy language 9.1. As you probably know by now, version 9 introduces an all-new compiler, and the compiler is significantly more advanced than any of our earlier compilers. At a high level, one of the main differences is that this is now a multi-pass compiler, and one of the main benefits of that is that it allows the compiler to perform much more syntax checking and code validation than was ever possible before. Synergy is now a strongly prototyped language, which essentially means that the compiler is now completely aware of all of the parameters for statements and external routines, and also of return value types for external functions. the compiler knows what's required and what's optional, what data type each parameter should be, whether parameters are arrays or not, which parameters are passed in, and which can be updated and returned. The benefit of this is that the compiler can now check that you're executing statements and calling routines in the correct way. This means that many things that would previously have resulted in unexpected behavior at runtime, or worse, errors at runtime, can now be trapped at compile time. Because of these changes, you may find that some of your code that compiled just fine under earlier versions will report warnings or even errors under the version 9 compiler. Don't be discouraged if this happens. In most cases, if you analyze the problem, you're likely to find a lingering potential bug that you may not have even known about. If you do have excessive problems when you first try to build with version 9, there are some things that you can do to temporarily relax this new additional checking, and we'll talk about these later in the presentation. So, strong prototyping is something that will help you write better code and have less runtime errors. Strong prototyping will check that you are passing enough arguments to statements and routines. It won't let you omit required arguments. It will also make sure that you're passing variables to arguments which can return information, and that you're passing appropriate data types to all arguments. Strong prototyping is implemented automatically for all system statements and external routines. This includes all of the various APIs in the language, the UI toolkit, SQL connection, etc. Basically, if it's part of Synergy, then it's strongly prototyped these days. Strong prototyping is optional for local routines, or in other words, your own subroutines and functions that are part of your application. Although optional, it's obviously a good idea to implement strong prototyping in your own APIs, in order to get the same benefits as with the system routines. It's simple. Strong prototyping improves quality. Strong prototyping is mandatory when you're developing and using classes. We'll look at how to implement strong prototyping in your own APIs later in the session. In order to achieve strong prototyping, the argument definition syntax needed to be extended to allow you to specify more information about the arguments to external subroutines and functions. Previously, the only things you could specify about an argument were a name, a data type, and whether it was an array or not. In version 9, you can now specify whether each parameter is required or optional, and whether data is passed in via the parameter, returned via the parameter, or both of these. You'll see some examples of this as we work through the rest of this presentation. We've also added several new end statements to the language. For routines, you can now specify end main, end subroutine, or end function. And for data structures, we also have end record, end common, and end structure. Generally, the use of this new syntax is optional. Really, they just help to make code a little bit clearer and easier to read. There are one or two places where using these new, more explicit end statements is required. One is with something new called global structures, and we'll talk about that again in more detail in a little while. And there are also some cases when using records in a class where end record would be needed, for example. By default, Workbench syntax expansion will not insert these new keywords for you at this point in time, so that your code will remain compatible with earlier versions of Synergy. However, if you are working solely on version 9, there is now a new option in Workbench which makes it insert this new version 9 syntax for you with keyword completion. A really useful new feature in version 9 is the new init statement, which can be used to initialize a data structure such as a record or a field. Init gives you an alternate way to using the clear statement, and the biggest difference is what happens when you clear a record or a group, for example. When clearing a record, the entire record is filled with spaces. This is obviously okay for alpha fields, and it's even okay for decimal fields because the runtime treats spaces in decimals as zeros anyway. However, if you clear a record that contains integer fields, you're likely to run into problems. If you use the init statement to initialize a record, it initializes each individual field correctly based on the type of the field. So alphas are set to spaces, decimals set to 0, and integer fields are set to binary 0 or null. Another nice thing about the init statement is that if the fields have initial values specified, then those initial values are also reasserted. Here's an example of the init statement in use. As you can see, the clear statement simply sets the entire record to contain spaces, whereas the init statement initializes each field and reasserts the two initial values. Another new statement introduced in version 9 is the data statement, which can be used to add a new local variable declaration in the procedure division. Data statements can only be used inside begin-end blocks and are used to define a new variable which has scope only within that block. The data statement must precede any other statements in the block, and the variable defined is treated as stack data, meaning that it is initially uninitialized, unless you specify an initial value, of course. You can use the data statement to declare real arrays, but not pseudo-arrays. A couple of things to be aware of. If you use the data statement within a loop and specify an initial value, then that initial value will be reasserted each time around the loop. Also be aware that it is possible to declare a local variable with the same name as a variable defined in the data division, thereby effectively hiding the original routine scope variable. On this slide you can see an example of a data statement, which is being used to declare a local loop counter variable within the begin-end block. Support for structures was added to the language some time ago, but until recently the only common use for a structure was in relation to allocating and accessing dynamic memory. In version 9, however, there are several new ways that structures can be used. Version 9 adds support for Struct Fields, which is a way of defining a field based on the layout of a structure. It's also now possible to use structures to define subroutine arguments, and there are some great reasons to do so, related to strong prototyping. We can also now declare both fixed and variable sized arrays of struct fields, and through the use of a little bit of OO code, we can also manipulate dynamic collections of struct fields. And other things, in fact. We'll look at these in more detail later. There's also a new type of structure, called a global structure. Here's an example of one possible use of a structure before we had support for struct fields. In the yellow box you can see that we have a structure called contact. Once we had a structure, we could define fields based on the size of that structure. So here, the size of contact 1 is determined by the structure, as is the field contact 2. We could then use #m to access the logical subfields within the contact 1 or contact 2 fields. This technique works great and could be very useful from time to time, but it doesn't exactly make for very readable code. In version 9, we fully support struct fields. Notice the differences between this example and the previous one. The fields contact 1 and contact 2 are no longer defined as a @size of contact, they are declared with a data type of contact. These are struct fields. Contact 1 is an instance of the contact struct. Also notice the difference in the way that struct fields are accessed. #m is no longer used. We can now directly access the subfields within the struct field using a normal path syntax. Although the end results are essentially the same, using struct fields results in much cleaner code which is easier to understand. There are also some benefits related to strong prototyping, but we'll get onto that a little later. It is also now possible to specify default values for fields in a structure. This was previously illegal. If a structure's field has initial values, then those initial values are propagated onto any struct fields which are based on that structure, and are also reasserted if those struct fields are initialized with the new init statement. It is also possible now to define and use arrays of struct fields. Once again, this doesn't really give us new functionality, but it does make our code much easier to write and maintain. It makes the code more readable, and of course there are benefits in terms of strong prototyping. Before the advent of struct field arrays, we could define an array field with a fixed number of elements and base the size of each element on the size of a structure. On this slide you can see that the field contacts is a 2-element array of alphas, each being the size of the contact structure. We could then use #m to address the logical subfields in each array element. The next slide will highlight just how much simpler it is to achieve these same results using an array of struct fields. On this slide, you can see the same code example, but reworked to use an array of struct fields. As you can see, the contacts field is now an array of 2 contact struct fields. Accessing this type of array is also much simpler. We no longer need to use the #m syntax. We can just directly access the array field using the same type path specification that we would use to access a field in an arrayed group. As well as supporting fixed size arrays of struct fields, we can also now have support for runtime sized arrays of struct fields. In the past, this functionality could be achieved using dynamic memory. This new feature will not replace all uses of dynamic memory, but it does provide an alternate, simpler mechanism which can be used in some cases. On this slide, you can see that we are defining a dynamic memory handle called contacts. Notice that the field is simply defined as an I4. Then we would use memproc to allocate dynamic memory, expressing the amount of memory to be allocated based on the size of a structure, in this case contact, and the number of records to allocate, in this case 2. Having allocated this dynamic memory, we could then use #m to access the logical records and fields in the dynamic memory array. Here is an example of a piece of code which has similar capabilities. As you can see, the contacts field is an arrayed struct field. However, the number of array dimensions is specified as £. This is a runtime sized array. As the name suggests, the number of array elements will be specified at runtime. The statement contacts equals new contact bracket 2 bracket is where we determine the size of the array and actually allocate the underlying memory. Again, the array is accessed using the path specification, just like with an arrayed group. The use of runtime arrays can replace some uses of dynamic memory, but not all. It's possible to resize a runtime array using another new statement, like the one we can see on the slide, but this simply deallocates the original array and allocates a new one, so any contents are lost. If you want to be able to dynamically resize while preserving data, then you would continue to use dynamic memory. Or you could use a new collection, but we'll talk about that a little later. Also new in version 9 is the ability to define global structures, which are structures which have scope throughout all the routines in a source file. Global structures can be defined anywhere in a source file as long as it's outside of any specific program or routine, and can be used in any routine in that file. This is one situation where the new optional end structure statement is required syntax. On this slide you can see a simple example of a global structure. As you can see, the structure is defined outside of the program and the subroutine, and can therefore be used in either routine. Another powerful feature added in version 9 is the ability to use a structure to declare a subroutine argument. Prior to version 9, if we wanted to pass structured information to a subroutine, we would probably use a group, as you can see here. We could then declare the subroutine argument using a group in order to gain access to the logical subfields in the passed argument. This approach works well, but there is now a better way to achieve similar results. Enter structure arguments. We can now use a structure to define a subroutine argument. In this example, you can see that the thisContact field is a struct field of type contact, which is then being passed to an external subroutine. The subroutine declares its first argument using the contact structure. It's a struct argument. As you can see, the syntax is significantly simpler than with the earlier group example, and we have an added benefit because the argument is now strongly typed. With an alpha argument, or a group argument, which is really just an alpha argument, any old alpha value could be passed. With a struct argument, calling routines must pass a struct field of the correct type. The next feature that I want to talk about does require the use of a little bit of OO code, but we're going to be using objects, not writing new OO classes. Synergy version 9 introduces a few predefined classes. These classes can be used in Synergy applications, not just in OO applications, in any application. One of these classes is called the Arraylist Class, which provides an easy way of managing collections. A collection is like a variable-sized array, but whereas arrays are fixed in size, collections can dynamically shrink and grow. You've been able to do kind of this thing with dynamic memory for some time, but collections make it much easier to achieve and have additional features that would be more difficult to achieve even with dynamic memory. If you've done .NET development before, then you may be familiar with the Arraylist class. The Synergy Arraylist class is modeled after the .NET class of the same name and has broadly the same capabilities. The Arraylist class allows us to create a collection of any type of object. So if we want to use it, for example, to manage a collection of records, then we need to use a technique called boxing, which simply takes a value type like an alpha or a decimal or a record and boxes it inside an object. So a boxed record is simply an object which contains the record. Here's an example of boxing a record. Actually, what we're boxing here is a struct field, but the results are essentially the same. First, you'll notice that we have a global structure called strContact. Then we define a struct field called contact based on that struct. We also define a variable called objContact, which you'll notice is defined at strContact. This is an object variable of type strContact. Here we're simply populating the struct field with some data, and this is where we box the struct field into an object by casting it with the @strContact syntax. We could then add the object objContact to a collection. This final statement shows an example of unboxing the object, this time by casting it with strContact, which allows us to gain access to the original struct field. As you can see, boxing is achieved by casting a value type to an object type. That's what the @strContact does. And unboxing is done by casting a boxed object back to its value type, in this case with the strContact, without the @sign. This slide shows the types of operation that you can perform once you've created an array list. The things in blue are either methods or properties of the Arraylist class. The add and insert methods add items to a collection. Add at the end, insert at a specific position within the existing collection. The count property lets you find out how many items are currently in the collection, while the capacity property returns the current maximum capacity of the collection. Collections will dynamically grow, so if you just keep adding items, the capacity will periodically increment. Or you can explicitly set a capacity to manually control the capacity of the collection. It's easy to locate existing items in a collection via the indexOf method, which locates and returns the index of the first occurrence of an item in the collection, or the lastIndexOf method, which locates and returns the index of the last instance of an item. Items can also be retrieved by a specific index number. If you wish to remove an item from a collection, then you can use the removeAt method, specifying the index of the item to be removed. And yes, it's perfectly valid to remove items in the middle of the collection, which in some ways conceptually behaves like a linked list. Here is a very simple example of using an Arraylist class. First, you'll notice that we've declared two variables. Contact is a struct field, and contacts is an object. It's an object variable for an object of type Arraylist. It's going to refer to a collection of contact records. This code creates the new collection, or Arraylist. Here you can see that we are sequentially reading records from a data file into the struct field contact. And here we are boxing the struct field into an object and then adding the object to the contacts collection. At the end of this loop, we will have all of the contact records from the data file in a collection, and we can then work with them as needed. As discussed earlier, Objects aside, perhaps one of the biggest changes with the introduction of Synergy version 9 is the strong prototyping capability of the new compiler. Strong prototyping is a mechanism which allows the compiler to perform much more validation and error checking than was possible in earlier versions, which in turn means that many more potential errors can now be detected at compile time, rather than at runtime. Prototyping is mainly concerned with guaranteeing that statements and routines are being used correctly, that the required arguments are being passed, that appropriate data types are being passed, and that variables are being passed when arguments can update and return information. Strong prototyping is facilitated by the creation of prototype files which contain information about the external interfaces of routines. These prototype files are exported using a new utility called dblproto, and they are then imported into code where those routines are being used. The best place to start with strong prototyping is with your standard subroutine libraries. We'll walk through the process in the next few slides. Strong prototyping requires the use of another new feature in version 9, namespaces. A namespace is simply a container which you can use to logically organize the subroutines, functions, and classes that make up your application. The use of namespaces is mandatory when doing OO programming and is optional with subroutines and functions, but it's required in order to perform strong prototyping. A namespace simply logically groups things together, perhaps by author company or application subsystem, or perhaps both. For example, you might use a namespace to logically define all of the routines that belong to a certain area of your application, such as the general ledger. Namespaces can also help avoid naming collisions. For example, you might have two external routines called post-payment, one in accounts receivable and one in accounts payable. Placing these routines in different namespaces helps to ensure that the correct routine is selected for use. Namespaces are hierarchical and can be nested within one another, as you'll see on the following slides. This slide shows the concepts of how namespaces are used. The outer cloud represents a namespace, and as you can see, there are several subroutines and functions which are members of that namespace. In an application, these routines might be generic routines which are used from all areas of the application. The two inner clouds represent two nested namespaces. Each is contained within the outer namespace, and each also contains subroutines and functions. These inner namespaces might contain routines that are used by a specific area of an application, such as perhaps the general ledger or the inventory subsystem. Namespace names are used in code, so picking meaningful names will help programmers to use the namespaces. Namespace names are very often based on company names or product names, and nested namespaces are often based on functionality of the items contained within the namespace. For example, if your company is called ABC Software, then you might choose to use that as your top-level namespace. And were you to develop a payroll application, you might choose to assign all of the software components of that application to the abcsoftware.payroll namespace. At the end of the day, the concept of namespaces is very important, but the actual names of the namespaces is less important. It's really just a naming convention. You may need to note that the top-level namespaces Synergex and System are reserved for internal use. The System namespace is reserved because of future compatibility requirements with Microsoft's .NET platform. Here's another example of namespaces in use. As you can see, the top-level namespace ABC Software contains routines which might be used throughout the company's suite of applications, while the abcsoftware.ar namespace contains accounts receivable specific members, and the abcsoftware.ap namespace contains accounts payable members. In order to use namespaces for strong prototyping of existing subroutines and functions, there are several ways of specifying the namespace to be used. A namespace is declared using the new namespace and end namespace statements, which surround any routine or routines which are to become part of that namespace. Ultimately, this is the best approach to take, as it makes it very clear when looking at a piece of code that the routine is part of the namespace. However, this does require editing each and every source file, and there may also be implications if you still need to be able to compile the code with earlier versions of the compiler, although you could get around that with the use of some defines and a couple of .ifdef compiler directives. If you prefer not to edit the code at this point, then there are three other options available to you. You could set the new environment variable sin-def-ns to the namespace that you wish to use. You would do this when exporting prototypes and when compiling the code. Or you could use the command line options when exporting prototypes for the code, or if you do nothing, the fallback namespace of sin-global will be used. These techniques allow you to start taking advantage of strong prototyping, but without having to make significant changes to all of your code at this point in time. Although to take full advantage of strong prototyping, you are going to have to enhance the code at some point in time. Once you've organized your subroutines and functions into namespaces, the next step is to create a prototype file for each routine. Prototype files contain information about the external interface of a routine, such as the number and nature of arguments, and for functions the size of the type of the return value. Prototype files are then exported using a new utility called dblproto. This utility reads the source code of a routine and creates the prototype file for the routine. You will need to initially create a prototype file for each routine, and then create a new prototype file for a routine whenever the external interface of the routine changes. For example, when arguments are added or deleted, or when a routine is deleted or a new routine created. Prototype files have a very specific naming convention, which for subroutines and functions starts with the name of the namespace and any nested namespaces, followed by the keyword sinRoutine, which prevents any possible clashes with classes or structures which also may be part of the namespace, followed by the name of the routine. The file extension of a prototype file is .dbh. Once you've created prototype files for all of your routines, you can then import those prototypes into the source files which use those routines using the new import statement. This is what enables the compiler to perform strong prototyping. Importing takes place at the namespace level, not at the individual routine level. This slide shows an overview of the entire process which is used to implement strong prototyping. The first step is to configure your environment. This could involve creating a directory to contain your prototype files. Typically, you'll want them to be stored all in one place. Deciding on the namespace or namespaces that you want to use, and perhaps setting some environment variables. With the environment configured, the next step is to enhance the declaration of each subroutine and function argument, specifying which arguments are passed, which are returned, which are required, and which are optional. Again, you'll need to consider whether you need to maintain backward compatibility with earlier versions of the compiler, and if so, you can use .ifdef dblv9 to make sure that these changes are only used by the v9 compiler or higher. Next, you'll use the dblproto utility to create your prototype files, and finally, update your source code to import the prototypes as required. If you've chosen to use a single namespace, then there are some techniques that can also help you avoid having to edit some of these changes into your code, and we'll talk about these in a little while. These are the three environment variables which can be used to define and configure the environment for strong prototyping. We've already mentioned sin-def-ns, which allows you to specify a default namespace to be used for any subroutine or function which has not been explicitly added to a namespace in the source code. Additionally, if you have sin-def-ns set, the compiler will implicitly import that namespace into each routine that you compile, enabling strong prototyping for all of the routines within the namespace. The sin-expdir environment variable is used to define the default location where the dblproto utility will create the prototype files. And the sin-impdir defines the default location where the compiler will search for prototype files when you import a namespace. Here we can see the extended syntax for argument definitions in external subroutines and functions. This new syntax is also used for parameters in methods. As you can see, you can now specify additional argument modifiers which define how the argument is used. For example, you can specify in if an argument is only ever passed in but never updated, out if the argument is only ever returned to the caller, or in-out if an argument is both received and returned. You can also specify whether an argument is required or optional. Some of these new modifiers may be abbreviated. For example, optional can be abbreviated to OPT and required to REQ. Here's an example of an external subroutine in which the argument declarations have been enhanced. The customer number argument is defined as required in. The compiler knows that the argument is required, so it will force a calling routine to pass the argument. But the compiler also knows that the argument is never returned because it's declared in, so it will allow either a variable or a literal to be passed. The compiler also knows that the data type of the argument is decimal, so it will enforce that a decimal literal or variable is passed. The customer record argument is defined as required out, and its type is a struct field. The compiler will not only enforce that a field is passed to this parameter, but it must be a struct field based on the customer structure. If you're using repository includes in your source code, then there are also similar enhancements to the syntax of the repository include, as shown on the slide. Strong prototyping really makes a lot of sense, and for most routines it's relatively easy to implement. However, you may have some routines which are difficult or even impossible to prototype. For example, it's not possible to prototype routines which have parameter lists which are totally variable or unpredictable in nature. If your application does include routines like this, then you may need to wrap those routines in .noproto and .proto compiler directives. This technique disables strong prototyping for the enclosed code and allows the enclosed routine to be defined and used as previously, but as part of an environment where other routines are strongly prototyped. To create prototype files, we use the dblproto utility, which reads source code and exports prototype files. It's a very simple utility which accepts one or more source file names. If you have a directory of source code, then you can export prototypes for all of the routines in the directory with the command dblproto star.dbl. By default, dblproto creates prototype files in the current directory, but this can be overridden with the sin.exp_dir logical name. Both of these can be overridden with the dblproto command line option -exp_dir. By default, dblproto assigns routines to the default namespace of sin global. We already discussed the fact that this can be overridden by using explicit namespace declarations in code or via the sin.defns environment variable. Another option for specifying the namespace to be used is dblproto's -out command line option. Here you can see an example of what a prototype file looks like. As you can see, the prototype file contains the prototype for the routine, which essentially consists of the external interface of the routine, the name, the argument list, and if the routine is a function, then the return value would also be detailed. Prototype files contain no specific implementation, however. There are no data definitions and no procedure division. Prototype files should not be edited by hand. They should always be created with the dblproto utility. The final step in implementing strong prototyping is to import the prototypes for a namespace at the point where the members of the namespace are used. This is achieved with the new import statement. The import statement imports all of the prototypes for a given namespace. All imports must be declared before any statements in a source file, and the scope of the import is the entire source file. This means that if a file contains multiple subroutines and functions, then the import is used when compiling all of those routines. Importing a namespace enables strong prototyping for all of the routines within the namespace. Importing a namespace does not import any nested child namespaces or any parent namespaces. The default location for importing prototype files is the current directory, and remember that this can be overridden via the sin.impdir environment variable. You can also specify the prototype file location via the directory qualifier on the import statement. If you have sin.defns set, then the compiler will implicitly import that namespace, but you may prefer to explicitly add the import statements to your code for the purpose of code clarity. Here is an example of two namespaces being imported into the program. The program may or may not use the routines from the namespace, but if it does, then those routines will be strongly prototyped at the point of use. Notice that the import statements do not appear inside the program's data division. They appear before the definition of the program, and would also apply to any external subroutines or functions that may follow the program in the source code. Another exciting new addition to Synergy version 9 is structured exception handling, and that's what we'll take a look at next. Using this new capability does require the use of some OO techniques and principles, but it does not require the writing of OO code. Structured exception handling provides a new and alternative way of dealing with error situations in our application code. This approach for dealing with runtime errors, or exceptions, is commonly used in many other programming languages. Structured exception handling is implemented via the new keywords try, catch, and finally. In addition to Synergy's traditional error numbers and the defined error literals that accompany them, each runtime error is now also represented by an exception class. These exception classes are organized into a hierarchy of exceptions. For example, there is an exception class which represents all file I/O errors, and there are exception classes which represent individual file I/O errors. When we write the exception handling code, we can choose whether to trap specific exceptions, perhaps a key not same exception, or a more generic exception like file I/O exception. When you catch an exception, the runtime hands you an exception object, and that object contains information about the exception, such as the error message and the error number. One big difference between structured exception handling and traditional error handling is that applications may define and throw their own exceptions also. Structured exception handling cannot be mixed with traditional on-error error handling within the same routine. As I previously mentioned, all of the Synergy exceptions are defined in a hierarchy, which allows developers to decide how granular their exception handling code will be. For example, to catch a record locked error, a programmer could define code to catch the specific exception, record locked exception, or to catch the more generic file I/O exception, which would catch any file I/O error, or the even more generic syn exception, which encompasses all of the traditional Synergy runtime errors. The developer could even catch the totally generic system.exception, which is the parent, actually in OO terms the base class, from which all exceptions derive. Exceptions do not have to be caught in the routine in which they are thrown either. Developers can choose to catch exceptions in a calling routine further up the calling chain, or even catch all errors in the mainline program. These capabilities, when combined, make structured exception handling very powerful and flexible. Here's what the syntax of a try-catch block looks like. The try statement is followed by the statement or statements in a begin end block, which may cause the runtime error to be thrown. This is then followed by one or more catch blocks, in which exceptions can be trapped and processed. You will notice that the catch statement is followed by the declaration of an object variable, and optionally a type. The type allows you to specify the type of exception that you wish to catch and process with this catch block. You will see some more complete examples of try-catch in use in subsequent slides. Remember that you don't have to catch all possible exceptions at the source of the exception, or indeed any of them. You may have code in a calling routine which catches some or all of the exceptions. Try-catch blocks can be nested one inside the other. Here's an example of a try-catch block in use. The code in the try block is the code which could result in an exception being thrown. The first catch block catches any protection violation exceptions which may be thrown as a result of the execution of the code in the try block. The second catch statement will catch any other Synergy I/O exceptions which may be thrown. If any other type of exception is thrown, it will not be caught, so hopefully another try-catch statement higher in the code will catch these exceptions. Otherwise, a runtime error will occur. In both of the catch blocks, the object variable name is declared as EX. EX can be used within the catch block and is an exception object containing data about the error. For example, the programmer could access ex.message to work with the exception's error message, or ex.errno to access the error number. Another useful aspect of structured exception handling is the ability to add a finally clause to a try-catch statement. If a finally clause is present, then the code which it contains will always be executed, regardless of how the try-catch statement is exited. In other words, regardless of whether an exception is thrown or not, the finally code will always execute. As mentioned earlier, another very useful aspect of structured exception handling is the ability for application developers to define their own custom exceptions. This does require a little bit of OO programming, but it's relatively straightforward to implement. Here you can see a custom exception class called Overbalance Exception, which is part of the mycompany.exceptions namespace. The exception class extends or inherits from a class called system.applicationException, which is a base class intended to make it easy for developers to define custom exceptions. Custom exceptions can contain application data, in this case the account number, credit limit, and account balance of a customer account. This exception can be thrown by code in the application, caught somewhere higher in the application's source code, and when caught, contains and exposes information about the event which caused the error to occur, the application data that was discussed earlier. Applications can generate exceptions using the new throw statement, which throws an exception object. So, to generate a custom exception, you create an instance of the exception that you wish to raise, and you throw it. You will see an example of this on the next slide. As an aside, it's also possible to process an exception multiple times, in multiple try-catch blocks at various levels in an application's code hierarchy. For example, you may wish to catch an exception at its point of origin, execute some error handling code in a catch block, and then rethrow the exception to be processed some more at a higher level. This can be achieved using the throw statement without an exception object. This is only valid inside a catch block. Here you can see an example of a piece of code which creates and throws the overbalance exception that we discussed earlier. As you can see, if the check account balance subroutine detects that an account is over its defined credit limit, then four things happen. First, the routine declares a new object variable called EX, which represents an overbalance exception. Next, the routine creates an instance of the overbalance exception class. It creates an object, and it specifies the customer account, credit limit, and account balance. Now, the exception's message property is set to account is over credit limit. We didn't see this property being defined earlier in code. In fact, it was inherited from the application exception parent class. And finally, the code uses the new throw statement to throw the exception object. This exception better be caught somewhere higher in the application's hierarchy, otherwise a runtime error is going to occur in the program. In the next section of the presentation, we're going to explore several new compiler options that are available with Synergy version 9, as well as a new technique that you can use to set default compiler options. We'll also briefly present some of the enhancements to the debugger in version 9. In order to assist with the migration to version 9, we've added a new compiler option called QRelaxed. This option can be used to relax much of the additional error checking that the version 9 compiler performs, over and above what the previous compilers used to do. The various options, deprecate, end, local, param, and path, can be individually used to back off the compiler's more stringent error checking in specific areas. These areas are perhaps too complex to cover in high levels of detail in a presentation such as this, so I'd recommend that you review the compiler documentation in the language reference manual before migrating to version 9 so that you know what to expect. The QRelaxed option is intended to provide temporary assistance with getting your code up and running under version 9, but not as a long-term solution. If you find it necessary to use QRelaxed, then ultimately you have a potential problem in your code, but the older compilers simply didn't detect it. We strongly recommend that you investigate anything requiring the use of QRelaxed, with the objective of identifying and resolving the underlying problem. Your goal should be to be able to compile your entire application without the use of QRelaxed. If you use OpenVMS, the compiler switch is /relaxed. We've also added a new compiler option called QStrict, or /strict on OpenVMS. This new option can be used to enforce strict out-of-bounds checking on runtime real array access. The functionality of QStrict is similar to that of the older QCheck, but without the relatively high overhead associated with using that older option. Synergex strongly recommends that all production code is compiled with the QStrict option enabled. We've also changed the implementation of the -w compiler option, which now gives you more granular control over the number and nature of compiler warnings that are displayed. A warning is not a serious error in the code, but is something which is at least questionable. As a general rule, many developers have a policy of not tolerating any compiler warnings. There are now 4 warning levels. The default warnings are represented by level 3. All warnings can be seen by changing the warning level to warning level 4, or certain types of warnings can be suppressed by reducing the warning level to level 2 or 1, or even level 0, which will suppress all warnings. For more information about the specific compiler warning levels and which warnings belong at which level, please refer to the language documentation. We also now support a new way of specifying default compiler options through the new environment variable syncmpopt. Any compiler options specified in this environment variable will be added to any command line compiler options before any command line options. This means that the default options can still be overridden on the command line if necessary. For example, if you decide you want to compile all of your sources with the new -qstrict and -w4 options, then you could achieve this by setting syncmpopt to contain -qstrict space -w4. And these options will be used each time you use the compiler, unless overridden on the compile command line. There were a significant number of enhancements to the debugger in version 9, many of which are related to debugging OO code. However, there were also a number of enhancements that can be used when debugging traditional Synergy code. The examine statement, when used on a record or a group or a struct field, now shows each field name along with its type and data. This can be suppressed in order to revert to the previous behavior using the new examine/a option. On Windows, the debugger window is now scrollable. By default, the previous 300 lines of output are preserved, but this can be tailored via the new environment variable dbg_buffer. There is also a new /page qualifier which allows you to page the output of the show, help, and examine commands. It's also now possible to record a debug session to a log file so it can be reviewed or analyzed at a later time. To start logging, issue the new command logging start followed by a file name, and to stop logging, use the command logging stop. There are some exciting new features in UI Toolkit also in version 9, and we'll take a look at these now. Version 9 of UI Toolkit introduces the ability to create and process composite container windows. A composite container is a single window which can contain other child windows. The composite container appears and is processed like a single window. Creating and processing composite windows is very similar to creating and processing tab sets. In fact, if your application already uses tab sets, then you may wish to consider switching some of those functions to use composite windows instead. And the process of doing so should be relatively straightforward. The primary difference between a tab set and a composite window is that with a composite window, all of the child windows appear visible at the same time and are visually part of the same parent window. Tabbing off the end of one child causes focus to naturally move to the beginning of the next child in sequence. One difference is that with composite windows, UI Toolkit provides default processing methods for each supported type of child window, so there may be less code to write when compared to tab set processing. The process for using a composite window is to create the composite container, add the children to it, if necessary, write a processing method for each of the children, and then process the container. In this presentation, we'll only take a brief look at the composite window functionality, as there is a separate Webucation presentation which goes into much more detail about this specific subject. Here you can see an example of a composite window in action. At the top of the window, there are two ActiveX List child windows, one showing customers, the other showing contacts for that customer. At the lower left of the composite window is a tab set child window with 3 tab pages. We can't see the first 2 tab pages, but they contain input windows with details of the selected contact. The third tab page shows an ActiveX graph control with the call frequency for the selected contact. The lower right is an ActiveX child window displaying a photograph of the contact. Composite containers support several types of child windows, including input windows, regular and ActiveX lists, tab sets, and ActiveX containers. Selection and text editing windows are also supported. It's even possible to add one composite window as a child of another composite window. UI Toolkit provides a default processing method for each supported child window type. These default methods provide basic functionality. For example, the default method for an input window processes the fields on the window and then moves focus to the next composite window child when the input window completes. The default method for a list window processes the list in selection mode and shifts focus to the next child when an item is selected. These default processing methods can, of course, be overridden in your code by naming your own custom processing method when adding a child to the composite window. As with the TabSet API, the Composite Windows API is very simple to use. In fact, it contains only 2 routines. The ccontainer routine is used to create composite container windows, add child windows, shift focus between those children, etc. Once the container has been created, the cProcess routine is used to process the container. This routine works in a very similar fashion to the TabSet API's tsProcess routine. It simply sets focus to the appropriate child window and calls that child window's processing method. We also added a new utility routine to UI Toolkit, which allows the more modern HTML help files, or CHM files, to be integrated with your UI Toolkit applications. As with the previous integration with Win32 help files, or HLP files, the routine has the ability to launch the help file in a variety of ways, to display the table of contents or to go directly to a specific help topic, for example, and also has the ability to perform help file searches programmatically. Professional Series Workbench also received attention in version 9, and we'll briefly look at those changes now. On Windows platforms, Synergy DE Professional Series version 9 now ships with SlickEdit version 11. The new Workbench now uses Synergy Language's core analysis engine, which means that Workbench now knows about and will continue to know about all currently supported language syntax. This also allowed us to remove several previous limitations, such as some things that didn't happen when group subroutine arguments were used, for example. Workbench version 9 provides full support for the enhanced syntax used to develop with Synergy objects throughout the tagging, indentation, and colorization engines, and fully supports Synergy OO development projects in Workbench's class browser window, which allows you to navigate your development project by namespace, class, field, method, property, etc. We've also improved several areas of colorization of various statements and routines, and have significantly improved the syntax expansion and code completion support within Workbench. It's also now possible to launch the new prototype generation utility, DBL Proto, from within the Workbench and have it create prototypes for all of the source files in your current development project. This new functionality is accessed via the Build menu. And for the xfnetlink.net developers, we've also enhanced the .NET component project types in Workbench to allow structure members to be generated as fields instead of properties, for performance reasons if you don't need the additional functionality provided by properties. And we also now support, through the UI, generating multiple instances of a class to support the creation of multiple discrete COM+ pools based on the same object type. As we work towards the initial release of Synergy DE for .NET, we've started to introduce some language features that will ultimately aid in your migration to that new platform. We'll look at these next. One of the changes we've made is we've introduced several new supported data types into the language, and more will follow. You can now define numeric variables as byte, short, int, long, and decimal. In current versions of Synergy, these new types directly correspond to the native Synergy types shown on the slide. For example, an int is directly equivalent to an I4. However, when the code uses these new types is moved to the .NET platform in the future, these variables will become those native .NET types. We also now support a string data type, which allows you to store and process variable length strings. If your longer term plans involve migrating to your Synergy applications to the .NET platform, then you may wish to consider periodically using the new -qnet compiler switch. When you use this new switch, the compiler will emit additional messages and warnings related to things that you may be doing in your code which will not be compatible with Synergy 4.net. This will help you to understand some of the changes which may be required in order to migrate to the .NET platform, and will allow you to begin to work towards that goal now. Now it's time to wrap up the presentation, but before we do, we'll tell you about some of the minimum requirements for operating systems and other related third-party products that you'll need to have in place in order to migrate to version 9. Synergy DE version 9 supports some new Windows platforms, namely Windows Vista in both its 32 and 64-bit variants, and Windows Server 2003 for x64 systems. Also, on Windows, we now enforce our minimum operating system requirements in the installer. The minimum required versions are shown on the slide, as are the minimum versions for the OpenVMS environments. Another addition to the supported platforms is that the SQL Connection product now supports MySQL databases on Linux systems. The MySQL version number must be 5024 or higher. This slide shows the minimum required operating system versions for the various Unix platforms supported by Synergy. If you need time to review this slide more closely, then please pause the presentation now. Before closing, I should also mention that the Synergy DE documentation set has received significant enhancements and reorganization for version 9, particularly in the language reference manual. There is of course a lot of new information relating to the use of Synergy objects, and the information about many of the ancillary tools, as well as the information about error messages, has been moved out of the language reference manual into a new Synergy language tools manual. There is also a new environment variables and system options manual. In closing, I'd like to remind you that version 9 includes an all-new compiler, which, as a result of strong prototyping, amongst other enhancements, is capable of finding and reporting many more things about your code than was ever possible before. There is a considerable amount of new syntax in the language also. As always, Synergex has made every effort to ensure compatibility with existing code, wherever possible, and rest assured that version 9 has been extensively tested with the full application suites of many of our largest customers. However, you should be prepared and expect that there may well be some minor changes needed to your code in order for it to compile successfully under version 9. Many of the things that the version 9 compiler may report when you first compile your code, upon analysis, will turn out to be potential bugs in your application that you didn't know you had. Remember that techniques like QRelax can help you get over the initial hump, but you should really set about addressing any issues which are reported. Your applications will be in better shape and will be more stable as a result of making this effort. Thank you for taking the time to view this presentation. If you have any comments or suggestions relating to this or other Webucation presentations, please communicate them via your Synergex account manager.